Okay, let's dive in. Ever just stare up at the night sky and have your brain do that little existential wobble? Like, where does all that space even come from and time ticking away? Is that just a fundamental beat of the universe, or could it be something,
Yeah.
oh, something we haven't quite wrapped our heads around yet?
What's fascinating and maybe a little mind-blowing for you to consider is that this very question, the one that might keep you up at night pondering the cosmos, is exactly what brought together some of the sharpest minds in physics at the 23rd Solvay Conference.
The Solvay Conference. Oh, that rings a bell as being, a pretty big deal in the physics world, like the Olympics of Smarts.
Huh, you could think of it that way. Yeah. These conferences have a real legacy. The first one, way back in 1911, was all about radiation and quanta, the early days of Planck and his groundbreaking work.
Wow.
Then
Okay.
there was the iconic 1927 meeting on electrons and photons. Picture Einstein, Bohr, Heisenberg, all in one room, hammering out the foundations of quantum mechanics. Pretty intense.
Right. I mean, just imagine being a fly on the wall there. So this 23rd one must have been tackling some seriously heavyweight questions to follow in those footsteps.
Absolutely. The theme was the quantum structure of space and time.
Hmm?
And the goal, as David Gross, the conference chair, put it, was to really dig into the most profound and central puzzles in fundamental physics today, especially the ongoing, let's call it spirited debate
Hmm.
between quantum mechanics and our understanding of gravity.
Spirited debate. I like that. It definitely feels like those two are always seeing eye to eye in physics. So what were they actually deep diving into about the quantum nature of space and time?
A central idea that took the stage was this concept of emergent space-time. Now, what that suggests for you is that space-time, the very fabric of the universe as we experience it, might not be a fundamental building block.
Uh-huh.
Instead, it could emerge from a more basic level of reality, a theory that doesn't even include space and time in the way we intuitively understand them.
Emergent. Like,
Yeah.
how does something that feels so fundamental just pop out of something else? Can you give me an analogy I can, actually visualize?
Okay, think about the smoothness of water. When you pour a glass, it looks perfectly continuous, right?
Yeah. Yeah.
But we know it's made up of zillions of individual H2O molecules. That smooth fluid nature we see is an emergent property. It arises from the collective behavior of those underlying particles.
Oh, okay.
Or consider temperature. It's not a property of single molecule, is it? It's a statistical measure of their average motion.
Right. Average kinetic energy. Yeah.
Exactly. So the idea with emergent spacetime is similar. Our familiar spacetime might be an effective description that arises from something much more fundamental and granular, something at a scale we can't directly see. The key insight here is that what feels continuous and fundamental to us might actually be a kind of large-scale approximation.
Okay. That water analogy, I think that's clicking. So what kind of something deeper are physicists actually talking about here? What's the potential underlayer? Is there a theory for this?
Well, one fascinating possibility that was discussed is something called generalized quantum theory. Now, for you to understand the significance, this is a framework that tries to capture the essence of quantum mechanics as it applies to closed systems like the entire universe, perhaps.
The whole universe. Okay.
Right. And it does this by stripping away any assumptions about a pre-existing space or time.
No space or time to begin with.
That's the idea. The crucial takeaway is that if your starting point doesn't require space and time, then they have the potential to emerge from the theory itself. Space and time become, in a sense, optional at the most fundamental level.
That's pretty wild to wrap your head around.
Yeah.
So the very stage on which the cosmic play unfolds might not even be necessary at the beginning.
That's the suggestion. And it's not just a random thought either. String theory, for instance, offers some intriguing clues that our everyday understanding of space might get. Well, a bit fuzzy at incredibly tiny scales.
Yeah.
We're talking around the string length and the Planck length. The key insight from string theory for you is that even in a theory that tries to unify all forces, the geometry of space isn't as fixed as we might imagine.
String theory, always pushing the boundaries of what I think is real. What kind of fuzziness are we talking about with space? Like, how does it get fuzzy?
Well, consider something called T-duality. What this tells us is that two seemingly different geometric setups in string theory, say, a universe with a very small circular dimension and another with a very large one, can actually describe the exact same physics.
Wait, really? Small is the same as large.
In this context, yes. It's like having two completely different looking rooms that turn out to be the same room if you have string theory goggles on. This suggests that our usual way of distinguishing between different spatial geometries might not be fundamental.
Okay.
Then you have mirror symmetry, where different, very complex shapes called Calabi-Yau spaces, you can imagine them as the intricate geometries of extra hidden dimensions.
Right, those folded up dimensions.
Exactly. So spaces with different overall shapes, different topologies even, can be continuously transformed into each other while keeping the underlying physics identical. The core implication for you is that the specific form of these spatial dimensions might not be a fundamental aspect of reality. Space, at this level, seems much more fluid and less rigidly defined than we experience it.
So space is getting all squishy and interchangeable at these super small scales. Almost like it's not a solid stage, but more like a really thick fog that can shift and change shape.
That's a vivid way to put it. Yeah, something like that. And there are other examples, like the Cigar-Liouville duality.
Hmm.
In that case, what looks like a curved space in one description becomes a flat space with a force field in another. It flips between geometry and potential.
Geometry because forces.
Effectively, yes. And the important insight here is the crucial role played by winding modes of strings. Think of how a rubber band can wind around a cylinder multiple times. The physics depends on these windings, highlighting that simple geometry isn't the whole story. The geometry and the forces acting within that geometry seem to be intertwined and even interchangeable in some situations.
Okay, my brain feels like it's doing yoga.
Yeah.
Seriously. But this idea of emergent space-time isn't just about space being this weird fluid thing, right? What about time? Does time get in on the weirdness too?
That's the next logical step. And it was definitely a topic of discussion. I mean, if space can emerge, why not time?
Yeah, seems fair.
It would certainly create a more unified picture at the fundamental level, putting them on equal footing.
Yeah.
There's even the concept in perturbative string theory of emergent time, linked to something called time-like Liouville theory. It actually has parallels to how spatial Liouville theory relates to emergent space.
So there's a symmetry there, potentially.
Potentially. The key takeaway for you is that the idea of time as a fundamental ever-ticking clock is also being questioned at the deepest levels of physics.
So the metronome of the universe might not be ticking at the most fundamental level either.
I mean,
It's unsettling, but also kind of amazing to think about.
it really challenges our deepest intuitions about reality, doesn't it? And it leads to another fascinating point that was raised. Maybe some of the fundamental principles we hold so dear in physics, like general covariance, aren't fundamental either.
General covariance.
That's
Remind me,
it.
that's the Einstein thing, right? The laws of physics should look the same no matter how you're moving or where you were observing them. No special viewpoints.
Exactly that. But if space-time itself is an emergent phenomenon, then maybe general covariance, which is so intimately connected to the structure of space-time in Einstein's theory of gravity, is also something that emerges, something that appears at larger scales, rather than being a fundamental starting principle. The fact that general relativity seems to lack truly local observables, things you can measure precisely at a single point in space-time, kind of hints at the possibility that a fundamental underlying space-time might not even be a necessary ingredient. The core insight here is that a principle we thought was bedrock might actually be a consequence of a deeper structure.
That makes a strange kind of sense. If there's no fundamental place or time to take a measurement from, then maybe the idea of the laws being the same in all places becomes less critical at that foundational level. It sort of loses its meaning.
Precisely the line of thinking. And there are even theoretical models that offer glimpses into how space might actually emerge. Matrix models of 2D gravity, for example, are these mathematical frameworks where space and even general covariance seem to pop out in the effective description, even though they weren't part of the initial ingredients.
Okay.
The key insight for you is that these simplified models provide concrete examples of how space can arise from something more abstract, like matrices.
Two-dimensional gravity. Is that like a toy universe, a simplified version physicists play with?
In a way, yes. It allows physicists to explore these complex ideas in a more mathematically manageable setting. It's a testing ground. And then you have the celebrated gauge gravity duality, often referred to as add-SCFT.
Ah, yes, add SCFT. Heard a lot about that one.
It's a really profound connection. It links a theory that includes gravity in a higher dimensional curved space, anti-de Sitter space, or ADS, and a quantum field theory without gravity living on its lower dimensional boundary, a conformal field theory, or CFT.
So gravity in the bulk space is related to quantum stuff on the edge.
Exactly. And the mind-bending part for you is that the extra-spatial dimension in the gravity theory seems to emerge from the dynamics of the quantum field theory on the boundary. It's like the shadow of a theory in one fewer dimension somehow creates the illusion of depth and gravity in the higher dimension.
So it's like a flatland scenario where the physics on the 2D plane somehow generates a 3D world with gravity. That's seriously cool and kind of confusing.
It is. It's one of the most powerful ideas in theoretical physics right now. And there are other examples like the BFSS matrix model. That model suggests that all the space-time dimensions we experience could potentially emerge from a relatively simple quantum mechanical system involving matrices, just arrays of numbers that obey specific rules.
Matrices.
Yes, matrices. The core idea for you is that space-time itself might be encoded in these fundamental mathematical structures.
Matrices all the way down. It's like we're living in the Matrix. Or maybe just a giant spreadsheet.
You could say that, perhaps. Now, this whole discussion about emergent space-time naturally leads to a deeper question. What about the role of quantum mechanics itself in all this? Is it the ultimate foundation from which everything emerges, or could it also be part of the emergent story?
That's what I always thought. Quantum mechanics is the rule book for the very small, right? And gravity needs to somehow fit into that picture. So is someone suggesting quantum mechanics might not be the final word?
Interestingly, yes. Some physicists at the Solvay conference, Strominger, for example, raised the possibility that quantum mechanics as we currently understand it might be fundamentally incomplete or even wrong in some way.
Whoa.
This might sound radical, but there are some deep puzzles that hint at this possibility.
Wrong. That's a pretty strong statement in the world of physics. What kind of arguments were made? Why question quantum mechanics?
Well, one key point he raised concerns the Big Bang. If you believe in unitary evolution, which is a cornerstone of quantum mechanics, saying information is always preserved,
Right. Things evolve smoothly, information isn't lost.
then the idea of a definite beginning of time for the universe becomes problematic. Where did the initial quantum state come from? It feels like it breaks the rule of being able to always evolve a state forward or backward in time.
Yeah, a starting point messes with that reversibility.
Exactly. He also pointed out a more subtle issue. The Schrödinger equation, the fundamental equation of quantum mechanics, treats time in a very specific preferred way. It singles out time,
It does, yeah.
which doesn't sit well with the spirit of general relativity, where space and time are supposed to be on a more equal footing, woven together.
Right, space-time, not space and time separately.
So the core insight for you is that our current formulation of quantum mechanics might have limitations when dealing with the universe as a whole and the nature of time itself.
That's a really thought-provoking point about the Big Bang. A true beginning Does seem to throw a wrench in the works of eternal quantum evolution.
It does, and Wilczek echoed some long-standing concerns about whether quantum mechanics is truly unified with the rest of physics. The rules for quantizing classical theories, the process of turning classical concepts into quantum ones, by imposing specific mathematical relationships like commutation relations.
Making things fuzzy and probabilistic.
Kind of. Those rules can sometimes feel a bit arbitrary, more like an add-on recipe than an intrinsic part of a deeper unified structure. He even mentioned how Planck's units, which combine fundamental constants like g, c, and h bar, could arguably be defined differently, potentially suggesting that Planck's constant itself might be something derived rather than truly fundamental.
Questioning H-bar. That's fundamental.
It's thinking outside the box. The key takeaway for you is that the way we currently do quantum mechanics might not be the most fundamental description available.
So maybe quantum mechanics isn't the ultimate basement level of reality either. It's layers all the way down, isn't it? Turtles upon turtles.
Some physicists think so. However, Seiberg offered a contrasting viewpoint. He emphasized that in string theory, quantum mechanics often seems to be deeply woven into the fabric of the theory itself, not just something you tack onto a classical system afterwards.
Oh, so string theory needs quantum mechanics intrinsically.
In many formulations, yes. He gave examples of certain types of fields and geometric configurations in string theory that don't seem to have a classical counterpart that you could quantize in the usual way. They are just inherently quantum from the start. The core insight here is that in some of our most advanced theoretical frameworks, quantum mechanics appears to be a fundamental and unavoidable aspect.
It's like we're trying to understand a puzzle where some pieces tell us one thing quantum mechanics is fundamental, and other pieces seem to tell us something slightly different. Maybe it's emergent or needs changing.
Precisely. It highlights the ongoing tension and exploration. And then you have thinkers like 't Hooft suggesting the possibility of a deterministic layer beneath quantum mechanics.
Deterministic, like classical physics again.
Sort of, but in a hidden way. And Penrose proposing that gravity itself might play a role in the mysterious collapse of the wave function in quantum measurements.
The measurement problem.
Exactly. These are all different perspectives on whether our current understanding of quantum mechanics is the complete picture. The key takeaway for you is that the very foundations of quantum mechanics are still being actively debated and explored. It's not settled science at that level.
This is all making my head swing in the best possible way. But how does this whole idea of emergent spacetime, maybe even emergent quantum mechanics, connect back to those really problematic singularities in general relativity? Inside black holes and at the Big Bang, where our current understanding of physics just breaks down.
That's a crucial link. Many physicists hope that a theory of quantum gravity, perhaps one involving emergent spacetime, could provide a way to resolve these singularities.
How would that work?
Well, the idea is that if spacetime as we know it doesn't exist at these extreme points deep inside a black hole or at the very beginning of the universe, then the breakdown of Einstein's equations there might not be such a fundamental catastrophe. If there's no spacetime, the equations describing space-time don't need to apply, right?
Okay, so the problem just dissolves because the stage isn't there anymore.
That's the hope. The key insight for you is that by changing our understanding of space-time at the most fundamental level, we might be able to bypass these problematic singularities. However, it's also important to note, as discussed at the conference, that modifications to Einstein's theory that could resolve singularities don't necessarily have to involve quantum mechanics. There could be classical modifications.
Oh, interesting. So fixing these cosmic potholes might be a non-quantum repair job.
It's a possibility, though most bets are on quantum gravity. But string theory does offer several specific ways that singularities might be resolved using quantum effects. Sometimes it involves these extended objects called branes appearing at the singularity.
Brains, okay.
Or it can happen within the mathematical framework of perturbative string theory itself. For example, the concept of a tachyon condensate phase in string theory.
Tachyons, faster than light particles.
Sort of. They represent an instability in the theory, but this condensation phase, which some connect to emergent time at an initial singularity, offers a potential mathematical way around the Big Bang singularity. It replaces the singularity with a different physical process.
So string theory has tools for this.
It has potential tools, yes. However, it's also important for you to know that not all singularities in string theory are resolved, or at least we don't yet understand how they might be. It's still a very active area of research. The key takeaway is that string theory provides potential mechanisms for resolving singularities by fundamentally altering our picture of space-time at extreme conditions. But the job isn't finished.
So the jury's still out on whether this emergent spacetime idea is the magic key to smoothing out all those cosmic wrinkles.
Exactly. It's a very vibrant field of research, and as David Gross himself pointed out at the conference, some of these very same fundamental questions were being debated with just as much intensity 70 years ago.
Wow.
We're still grappling with the deepest aspects of reality. The conversation continues.
Wow. It really makes you reconsider what we even mean by real. The possibility that space and time, the very scaffolding of our universe, might be emergent. That's a real aha moment, isn't it?
It absolutely is, and it has profound implications for how we understand gravity, cosmology, and the ultimate origins of the universe. If space-time isn't fundamental, how do we reconcile that with Einstein's beautiful geometric theory of gravity? Could this be the missing piece in the puzzle that finally unites quantum mechanics and general relativity? These are the big, exciting questions driving this research forward.
So next time I'm looking out at the world or just, checking my watch, I should probably remember that what feels like solid ground in the steady march of time might be something far more subtle and interconnected than I can even imagine. Maybe a collective dance of something we can't directly perceive.
That's a beautiful way to put it. Perhaps our everyday experience of a continuous, fixed space-time is indeed a kind of emergent phenomenon, a macroscopic approximation of a much more fundamental, maybe even discrete and dynamic reality that we're only just beginning to glimpse. It certainly gives you a lot to ponder about the very nature of existence, doesn't it?